Differentiation is mostly syntax-directed. At a sum, use the sum rule. At a product, use the product rule. At sign, use the sign rule and continue into its argument. Each step creates a finite set of smaller derivative tasks. Integration asks the reverse question. One visible form may have come from substitution, integration by parts, an identity, or no expression in our language at all.
So why start with the direction we already know how to compute?
Because a hard answer can still be easy to check. If a search proposes an antiderivative, differentiate it, simplify it, and compare with the integrand. The forward language becomes an independent verifier. It can also generate unlimited known-good problems by differentiating expressions we choose. Derivative knowledge fits the rule language we just built. The derivative of x is 1. The derivative of a numeric constant is 0. A sum produces two derivative children. A product produces two products. Sine produces cosine times the derivative of its argument. And a square produces 2 times its base times the derivative of that base. Each pattern matches a derivative node. Its replacement is another symbolic expression, often containing smaller derivative nodes. The rewriter keeps expanding until no derivative operator remains. Then the simplifier runs as a separate pass. Separation matters. Derivative rules encode calculus, while simplification rules encode normal form. Differentiate sine of x times x squared. The product rule expands the root into two terms. On the left, the sine rule creates cosine of x times the derivative of x. On the right, the square rule creates 2 times x times the derivative of x. Both leaf derivatives become 1. The remaining tree contains no derivative nodes. Now the shared simplifier removes multiplication by 1, orders factors, and preserves the two-term sum. The normal form is x squared times cosine of x, plus 2 times x times sine of x. A numerical finite difference check at 4 points agrees to better than 100,000th. The spoken identity, the tree, and the executable fixture are the same object. To generate a valid integration problem, choose the answer first. Choose x cubed and differentiation gives 3x squared. Choose sine of x and it gives cosine of x. Choose sine of x squared and the chain rule gives 2x times cosine of x squared. Hide the chosen expression. Hand only its derivative to a solver, and the pair remains guaranteed by construction. This direction is useful for tests, benchmarks, and training data, but it must not be confused with solving the inverse problem. A generator knows the hidden source because we chose it. An integrator sees only the derivative and must recover some valid antiderivative. Our last generated pair becomes the capstone. Integrate 2x times cosine of x squared. The verifier is deliberately separate from candidate generation. Candidate 1 is sine of x squared. Differentiate, simplify, and we recover exactly 2x times cosine of x squared. Structural comparison succeeds, and every numerical residual is 0. Candidate 2 is sine of 2x. Its derivative is 2 times cosine of 2x. The structures differ, the numerical probes disagree, and the verifier rejects it. Checking does not tell us how candidate 1 was found. That is a feature. A generator can be heuristic, incomplete, or adventurous, while the verifier stays small and trusted. Next, we reverse selected rules. Expose all the alternatives they create, assign costs, search a bounded frontier, and send every promising result through this independent differentiation loop before accepting it.